In the previous video, we have talked about how to call a subroutine and how to return from a subroutine. In this video, we'll talk about how to pass arguments to a subroutine and how to return results from a subroutine. When we write assembly program, we have to follow the procedure call standard, which typically is part of the standard of application binary interface. The procedure call standard is a contract between a caller and a callee. Why do we need to follow the procedure call standard? Here, we give two important reasons. First, it allows subroutines to be separately written, separately compiled, or separately assembled, but work together. Second, it allows a C function to call assembly subroutine, or vice versa. In this video, we'll focus on the call convention, which defines how to pass arguments to a subroutine and how to return a result from a subroutine. The first four registers, including R0 to R3, are used to pass up to 4 arguments to a subroutine and return at most one value back. If each argument has less than 32-bit, we can pass up to 4 arguments via these 4 registers. If we have more than 4 arguments, extra arguments are passed to the subroutine on the stack. If an argument has 64-bit, it will be passed via 2 consecutive registers, such as R0 and R1 or R2 and R3. The most significant 32-bit are stored in register R1 and register R3 in this example. If an argument has 128 bits, it will be passed via 4 consecutive registers, with the most significant 32-bit stored in register R3. We can only return at most one result from a subroutine. The result must be placed in register R0 if it has less than 32-bit, in register R1 and R2 if the result has 64-bit, and register R3, R2, R1, and R0 if the result has 128-bit. Here is an example. This C function takes 4 arguments and returns a 32-bit signed integer. Since each argument has less than 32-bit, each argument is passed via a register. In this example, the first argument is passed via register R0, the second in R1, the third in R2, and the fourth in R3. When this function returns, it saves the result in register R0. The caller should find the result in R0. Let's see how we can translate this example into assembly. Suppose we need to calculate the average of 4 integers. If the sum function is implemented in C, we can call this C function in this way. First of all, we should put the arguments in register R0, R1, R2, and R3. Then we can call this C function sum using the instruction BLSum. Based on the procedure call standard, we know that the C function returns the results in register R0. Therefore, we can use sdiv to calculate the mean. On the other hand, if we have this C program, we can implement the sum function in assembly. We know that when a compiler builds the C program, the compiler will place these 4 arguments in register R0 to R3, that the assembly function can directly read these registers to obtain the arguments. In addition, the assembly function follows the procedure call standard and saves the results in register R0. Here is another example. This example calculates the sum of 2 64-bit integers. The argument A is passed in register R0 and R1, with the most significant 32-bit in R1. The argument B is passed via register R2 and R3, with the most significant 32-bit in R3. The 64-bit result is returned to the caller via register R0 and R1, with the most significant 32-bit in R1. We can implement this C function in assembly. This assembly function can be called by a C program because the C program also follows the program call standard to pass arguments and receive the results. We can only pass at most 4 arguments using the first 4 registers. Extra arguments have to be passed on the stack. Let's quickly review stack. ARM Cortex-M uses full descending stack. The stack pointer decreases as values are pushed onto the stack, and the stack pointer increases as values are popped off the stack. It's called full because the stack pointer points to a valid value of the stack instead of an empty spot. Let's use a simple example to illustrate how to pass extra arguments via the stack. In this example, this function calculates the sum of 6 integers. The first 4 arguments, A1 to A4, are passed via register R0 to R3. The last 2 arguments, A5 and A6, needs to be passed via the stack. Suppose we are making this function call to calculate the sum of these 6 integers. Here we show how an assembly program called this function. In the assembly program, the last 2 arguments, 5 and 6, are pushed onto the stack. Suppose here is the stack initially. After 5 and 6 are pushed onto the stack looks like this. In addition, the caller places the first 4 arguments in these 4 registers before it calls the subroutine sum6. In the subroutine, we first calculate the sum of first 4 arguments. Then we use the load register dual instruction LDRD to read 2 words from the stack. This instruction reads the last 2 arguments into R1 and R2. The subroutine cannot use pop instruction to obtain the last 2 arguments because the subroutine should not modify the stack of the caller. Then we'll continue to add these 2 arguments into register R0. After the subroutine is completed, the caller increments the stack pointer by 8 to remove the last 2 arguments from the stack. Here is a quiz. You can pause the video now and find out what's wrong in the assembly function. The assembly implementation has 2 errors. First, the sum should return in register R0 rather than R3. Therefore, we need to copy the value from R3 to R0. Second, it did not call BXLR to return the control back to the caller. Thank you for watching.